I see I have a smaller group today, this afternoon than this morning. Well, there's a good reason for that, because my talk, this one is going to be boring. So that's the first warning. If you want to have a talk with nice images, that's going to be next door. This one is about image processing. No images really. It's more about programming. So that's a kind of upfront warning. But if you want to stay, you're going to learn something very important on how to include your own C code or other people's C code in Mathematica so that it runs just as native code in Mathematica. So it's a very powerful technique I'm going to talk about, but it's going to be a little harder to digest than beautiful pictures. Secondly, I hope, this computer bears with me, because my computer that I used this morning is dead. So I'm working on somebody else's computer, and in case you see a beautiful woman at the desktop here, it's not my girlfriend. It's the girlfriend of my colleague, Julia. So what's LibraryLink? LibraryLink is an interface, program interface in Mathematica that allows you to hook up dynamic link libraries into Mathematica so that you can share code and, more importantly, data directly with Mathematica itself. Before I will dwell on that a little bit more in detail, I quickly switched to another option that you have in order to connect programs, and that is MathLink, or let's put it this way, formerly known as MathLink. Now it's known as Wolfram Link, or the Wolfram Symbolic Transfer Protocol. Now what that is the following. Mathematica usually consists of two parts. You have the front end, you have the kernel, and you have a protocol communicating between those two constituents. And that protocol is MathLink or Wolfram Link or WSTP. Now that protocol can also be used to communicate with other programs like a C program or a Java program. And that way you can very nicely hook up other programs to Mathematica as a master-slave combination or peer-to-peer combination. All of this has benefits. The benefit is you can have them on different machines. If one program crashes, the other one doesn't. So there are some merits to that. But there's one big drawback. And the big drawback is if you have a large piece of data that you like to work on, and your external program has to do some steps, and then your Mathematica has to do a few steps, you would have to copy all the data from Mathematica over to that external program and back. And of course, that may not be a very feasible approach if what you do is done very quickly. So this is basically the major argument why we have this talk here today, is to have another option or to work around this with LibraryLink and not to use MathLink. Okay, so before I will explain any abstract concept of what LibraryLink is, I simply explain how you use it by running an example. Well, first thing you would have to do is you would have to load a package, the C compiler driver, which allows you to compile C code from within Mathematica and which allows you to hook up to LibraryLink packages. Has, first of all, this function call, which is always basically the same. Here you have an argument which allows you to hook up to callback functions. Then you specify the number of arguments, which is done automatically for you. Then you have a list of arguments that's being passed, and you have an argument which is being returned, the result. And what you really have to care about is the internal of that C function, basically declare variables. You may have forgotten how to do that using Mathematica, but if you go back to C, it's one of these many tasks that you have to take care of yourself. So you declare the variables like the integer coming in, then you have an integer going out, and then you actually have to get that integer coming in, and that is done by one of those many callback functions that you have in LibraryLink. In this case, it's called the margument function _getInteger, which allows you to import an integer. Of course, you have then also getReal, getComplex, and other appropriate callback functions. Once you have that number, you add 1, and then you have to send everything back. So that's the margument setInteger command. Basically, that sets that result, that value of I1 into the result variable, and then if everything works okay, you basically would like to return a flag that says everything has worked, so you send back the flag library no error, and that's basically an integer that you send back. Okay, so that is all you need. That's your external library function. And what you would do in order to get going, you would have to declare all kinds of things so that this code would work. For the most part, it's defined up here in this header file, which you have to include. It's the Wolfram library.h header file for C that allows you to, that declares all the functions that we need down here. Then what you declare is a version function, an initialization function, basically nothing here to do, and an uninitialization function that's being called once you uninitialize that library. So in both of these cases, initialization and uninitialization, all you have to do is really copy-paste these examples, because in most cases, in most scenarios that you may run into, you don't have to initialize anything or uninitialize anything. So once you have done this code, and I have just stored this here as a string under code 1, so just to show that nothing is up my sleeves. So that's just a string with the C code. All I do here is I say create library, so I can basically compile it from within Mathematica using the default C compiler on your machine. And it compiles here a link library called libadd1, so that would be the name of the file, .dylbib or DLL, whatever machine you're on. And in Mathematica, I have a handle to that with this variable. It's called add-on library, add1 library. And then in order to basically call that particular function out of that library, I would have to use a library function load, specify the library where I find it, specify the string of the function call, so that's actually here the name of the function specified up here. And then I have to specify what goes in and what comes out. I basically pass over one integer value and get back one integer as well. So I evaluate this, then it shows me that I have here library function, and this is all I need to do. Now I can readily use that C code from within Mathematica. I can have here add 1 to 5, or I can map this function. I get then 1, 2, 3, 100, and so forth. And once I'm done, if I want to, and of course that also happens if you quit Mathematica, I can unload this function, this library, and once I have done so, this function call is no longer available. It would give you an error. Okay, so this is a basic scenario how you can use LibraryLink, and of course you can already envision which way we are going. Passing just integer is of course peanuts. It would not require a lot of overhead to pass this along, but if you want to pass a whole image, you can now here pass only a reference, and that would be sufficient. You don't have to copy it. So I have here another scenario. Basically, that was the scenario now in version 9, how you would, again, use LibraryLink to do some image processing. And without going into detail here, what I have is a function called Histogram 256. It's basically a very simple histogram function that takes integer data from 0 to 255 and counts how many corresponding integers you have from 0 to 255. And basically the data that comes in is not specified here, it's specified further below. It's an array. So instead of having a get integer, I have here get a Mathematica tensor. That's basically given in the first argument. Then I have to get the integer, the type. So I have to find out if it's a real valued array or an integer array and so forth. And in this particular case, I only accept integers, so I have to verify if the type that's coming in is actually an integer type. If not, I have to return an error. Then I basically flatten the whole data. First of all, get the length of the data, and then I just basically read out the data with this command. So data here is now a pointer to the data coming in. And here I have to explicitly generate a new array, since an array is not something that you keep in stack but have in the heap. You have to create and delete these arrays. So I have to create here a new array with mtensor, It's an integer array of the corresponding dimensions of a histogram, and then basically down here, I have a loop that goes through the image and basically populates the histogram. And once that's done, all I do is return a tensor, and that's my histogram. So let's see if that works. Again, the code is given now here in code 2. I compile it, I link it, and now I take an image. And now the unpleasant or not so nice part here is that, of course, I specified that for an array, not for an image. So what I had to do in order to use that in Mathematica, I had to first extract the data, convert that into an ordinary Mathematica array with image data, for example here, and then that data I could fuel into the histogram and would get the result instantly here. This is my histogram of that image. So the drawback at this point, still in version 9, simply was the fact that you could not use directly the image object in Mathematica, but that you had to convert that to an array of integers, reals, and so forth in Mathematica up front. So the benefit wasn't really there of having to move things. And now, that's the reason for the whole talk here is, of version 10, you can directly access the arrays in an image or image 3D object. And before we go into the details here, I quickly have to remind you that there is more to an array than just, more to an image than just an array of numbers. First of all, these things come in different data types, something you don't worry about in Mathematica too much, but you have images of bit type, byte type, bit 16, real 32, and real. So you have to distinguish those cases, of course, as you move them across, or if you work on them in your C code. Furthermore, images come in different numbers of channels, so you have to be aware, you have to make sure that you can handle an arbitrary number of channels. They can be interleaving or planar, meaning, well, in this case, this one, for example, is interleaving, saying that if you have several channels, then every pixel here, every element of the array has 3 values. That's interleaving. If instead you basically have 3 arrays, one for red, one for, actually this should be blue and green. Actually, I have RR, should be RGB. That is a planar configuration. And of course, also that would be something you have stumbled across if you work on this data with your C code. Then be aware that Mathematica supports all kinds of color spaces, so the encoding may be different. And last but not least, images also come with alpha channels. So if you have an alpha channel, that's actually usually the last channel in your image. That may be very well a channel that you'd like to treat differently than the other color channels in an image. So having said that, we can proceed. And I'd quickly like to point out that instead of now having to specify integer or array, you have here now a library data type. Oops, that should not say sparse array, that should have spaced image. Help me, how do I get back? How do I get out of this? Okay, here we go. Well, instead here it should read actually image data. Sorry, this is a previous version because of a backup issue. You have to specify how arrays are handled between the library and Mathematica, because you can have arrays that get deleted once they have been used automatically. You can have arrays that you specify as constant so that your external library or Mathematica cannot mutilate them in any way. You can declare them as shared or whatever. So these are all properties that you give your arrays or images in order to make sure that the memory doesn't just get discarded accidentally, or that it doesn't get discarded automatically to avoid a memory leak. Similar things apply to the images that you return, if they are sustained over a longer period of time or if they just disappear eventually. And once all of that is taken care of, you can write your little C programs. Here is a little program that does just a color negate. Again, you declare here the initialization, the uninitialization, and then here you have a slightly more complicated C program. It's written in C++ using templates, because you don't have to, but in most cases you probably like to, handle all kinds of data structures. So here for the color inversion, I have to make sure that if I invert the color, I subtract, for example, byte images from 255, whereas binary images, I just have to subtract them from the value 1. Bit 16 images, I have to subtract them from the value 65,535, and so forth. So I have here a template to handle all these kind of different scenarios of different data types. And the actual, let's see here, the actual command is down here. Where is it? Here it is, color negate, that's the function call. Color negate basically loads in the image array and the 0 argument, makes a clone of that image array because you actually want to generate a negated image. The clone basically has a property that it takes all the properties of an image and creates an image that has the same properties again. So it's just a clone, and then you can populate that clone with the result that you're calculating here. And the result you're calculating down here is done in this switch. The switch changes as the type changes of your image. The type can be bit, byte, bit 16, and so forth. And depending on that, you then call up here another template function, iColorNegate, for bytes, unsigned bits, unsigned bit 16s, and so forth. And that is specified up here. Whoops, well, sorry, I don't scroll correctly. That template function was specified up here. And that basically performs the color negation. So let's see if this works. So I create the library, I link up the command color negate, color with a small c, so it's not the built-in color negate. Here I have a grayscale image that I can negate, and obviously it worked without having to transform that via image data. And I can also take here an RGB image that works. And if you were looking closely, I specified this not just for images, but also for image volume, image 3D. So whatever I've done now, since it was not specific to any number of dimensions, I can do now also to volumes. So if I come up with a data volume like this one here, it automatically switches the color as well. All right, and then again, unload, and that terminates the example here for images. I have here another example, which unfortunately doesn't run now on this machine, because it requires a third-party library, which I don't have installed, and that is the LibRaw library that allows you to import all kinds of raw camera data, something that you may be lacking. And that's basically a main message. There's a ton of code out there, C code and C++ code libraries, that you can now easily attach to Mathematica and add that functionality to Mathematica. And in this case, you just can use it to to actually, yeah, well, I deleted the output, unfortunately, to import raw data into Mathematica and then to process that there. Okay, so that's basically it. Final remarks. The message of this talk is threefold. First of all, LibraryLink is ideal for users who like to speed up their own image processing commands because, well, it's an open secret. In Mathematica, it's an interpreter language. You can get close to the speed of C by a factor of 3, 4, sometimes if you're really good. Mostly it's a factor 10 difference. But if you have the opportunity now to actually code the most inner parts of your algorithms directly in C, you can really harvest that speed, and thereby you can really speed up your image processing code quite a bit, because you can also apply, for example, AVX or other vectorization primitives in your code to really utilize your hardware to the limit. Then, secondly, you can incorporate your C, C++ work that you may have done previously into Mathematica. That works very nicely. You don't have any overhead, so when you call these functions, you have an imminent response. And last but not least, as I mentioned, there's lots and lots of open source code out there that can now easily be incorporated in or included in Mathematica such as OpenCV, ITK, MTK, and so forth.